Hello and welcome back to HK Academy. In today's video, we will explore the open loop behavior of the boost converter using two LTspice models. An averaged continuous conduction mode model for fast analysis of duty to output behavior, transient response, and small signal dynamics. A full switching model with PWM modulation, MOSFET driver, diode conduction, and realistic ripple. These two models form the foundation for understanding how a boost converter behaves before we close the loop with voltage mode control. In upcoming videos, we will move to loop gain design, compensator structure, and finally digital implementation using C2000 microcontrollers. Let's start with the averaged boost converter. Here is the averaged boost converter model used in LTspice. This model is built around the HK underscore CCM1 underscore AVG block, which represents the ideal duty cycle behavior of a boost converter operating in continuous conduction mode. Because the switch and diode are replaced with their averaged equivalents, there is no PWM ripple. The inductor and capacitor see only averaged voltages and currents. This makes the simulation extremely fast and perfect for analyzing DC gain, low transients, and small signal behavior before moving on to a switching model. In this example, the converter steps 12-volt input up to 24-volt on the output. On the input, we have inductor and its series resistance, and on the output, a capacitor with its own ESR. The load consists of a static 480 ohm resistor, and every 2 milliseconds, starting from 4th millisecond, we apply a load step of plus minus 50 milliamps. We can run both transient and AC simulations with this setup. Let's start with the transient response. In this demonstration, we will show the output voltage response, and we can also show the average value of the inductor current. And the simulation runs 10 milliseconds, and now the simulation is finished. As you can see, we get the clean startup transient and then periodic load steps every 2 milliseconds. Because this is an averaged model, the waveforms are smooth, so there is no switching ripple, no high frequency noise. To achieve roughly 24 volt from 12 volt input, the required duty cycle is close to zero point 0.5. Here we can clearly observe how the output settles, how the inductor current behaves, and how the system reacts to small load disturbances. This makes the averaged model an ideal tool for validating the steady state gain and dynamic behavior of the boost converter. If we zoom now the output voltage of our boost converter, you can observe that the value is very close to the 24 volts, but it is not exactly the 24 volts. And it shifts with each load step. So here is a little bit higher value, a little bit lower, and so on. This illustrates why we eventually need closed loop control to correct these deviations and maintain a stable output. So let's now switch to the AC analysis. First, we need to put the semicolon here in front to disable the transient simulation. And then from here, we need to remove the semicolon. And now we can run the AC simulation. And here we just observe the output node or the output voltage. By measuring or observing the output voltage, we are actually measuring the GVD transfer function or the control to output transfer function, which is actually used for our compensator design. First, what you can notice is the DC gain, which is approximately 33.5 decibels. Then the right half plane zero, the most important dynamic feature. As the frequency increases, the gain curve begins to bend and the phase drops rapidly here. This behavior is dominated by the right half plane zero, which is unique to the boost converter. Unlike a normal left half plane zero that adds phase, the right half plane zero behaves like this. It adds the plus 20 dB per decade gain, but reduces phase by minus 90 degrees instead of adding plus 90 degrees. So it increases the magnitude but hurts stability by adding phase lag. This is why boost converters cannot run with high crossover frequencies. The right half plane zero limits the maximum achievable bandwidth. A typical rule of thumb is one fifth of the frequency of the right half plane zero. Next, we see the effect of the LC output filter. Magnitude drops by minus 40 dB per decade, and phase moves toward the minus 180 degrees. This is the classical second order behavior of a power stage with an inductor and a capacitor. At a higher frequency, the output capacitor ESR introduces zero. You can recognize it in the body plot by the magnitude slope becoming less steep, as shown here, and the phase shifting upward slightly. The ESR zero helps the phase a little, but in a boost converter, the right half plane zero and the LC double pole dominate the dynamics much more strongly. Still, the ESR zero is important because it marks the beginning of the capacitor's transition from an ideal component to a resistor dominated component at high frequency. In this simulation, you can see that the ESR0 occurs in the upper kilohertz range just before the plot rolls off toward very high frequencies. This AC response tells us everything we need for our compensator design: the DC gain, the right half plane zero location, the LC double pole, and the ESR0 at high frequency. Let's now switch to the full switching model. Here is a switching boost converter simulation. All the passive components, the inductor and the series resistance, the output capacitor and the ESR and the load are exactly the same as in the averaged model. The key difference is that we now replace the averaged CCM block with the real switching elements: a MOSFET, a diode, a 200 kHz PWM modulator, and a MOSFET gate driver block. This means that unlike the averaged simulation, we now see full switching ripple, diode conduction, and all the real switching dynamics of a practical boost converter. Let's now run the simulation. We will observe the output voltage, we will observe the inductor current, and we can also observe the PWM pulses as well. For this simulation, we again run a 10 millisecond transient. Just like before, starting at the 5 millisecond mark, we introduce periodic load steps of plus minus 50 milliamps at every 2 millisecond, so we can compare the averaged model and switching model side by side. At the startup, here you can notice that the PWM modulator begins switching after roughly 200 or 250 microseconds. Before that, the converter behaves like a simple diode feed RC network, which is why you see the inrush current charging the output capacitor through the diode. This is important practical detail. In a real boost converter, the input is directly connected to the output through the diode at startup. This causes a large inrush current unless proper hardware inrush current limiting is used, something that is not required in buck converters. Let's now zoom the output voltage here. We see the same behavior we observed in averaged model. The steady state output is close to 24 volt, as you can see here. Here is the line of 24 volt. It is not exactly 24 due to the conduction losses and the natural open loop boost characteristics, and it changes with every load step. Since this is an open loop boost converter, the output voltage cannot regulate itself, which is exactly why we need a closed loop voltage controller. This switching simulation gives us the real behavior, including the MOSFET switching ripple, diode conduction intervals, inductor current ripple, and the real dynamic performance under load steps. Both simulations tells us the same story, just at different levels. The averaged model is great for understanding small signal behavior and designing the control loop. The switching model is essential for validating real ripple, duty cycle behavior, and verifying hardware-like dynamics. Before we finish, here is a quick look at the free resources on HK Academy. If you want to experiment with boost converter simulations without starting from scratch, you can download my free boost converter toolkit. It includes LTspice models, Octave scripts, and example setups. Feel free to try it out and explore how the converter behaves. The link is in the description below. In the upcoming video, we will close the loop and look at how voltage mode control works for the boost converter, including the impact of the right half plane zero on the compensator design. Thank you for watching and see you in the next video.